So let's first look at the Assam earthquake of 1950s. So although the epicenter of Assam earthquake did not fall inside the Myanmar's territory, you can see from the map to the right, the felt area are almost covered entire Myanmar except for this long tail of the Myanmar between the southern Myanmar and the northern Thailand. And in the northern part of Myanmar, the intensity may reach to intensity 7 or even intensity 9, which means that it may cause a severe landslides as well as liquefactions to those villages in the northern Myanmar. And those pictures to the left are the photo that taken inside India showing how the damage looks like after the Assam earthquake. And as you can notice that most of the earthquake damage in this area is associated with the landslide as well as the liquefaction. For example, here you can see sand is blowing out along the crack next to the railroad. This is because of liquefaction in the Assam Valley. And the train was sinking down into the ground. That is also because of liquefaction, like causing the heavyweight material sinking into the ground. And the lower panel of photo showing a bungalow building has been deeply affected by the landslide. And that's also a very important phenomenon happened in the Assam earthquake. Although personally I did not work on the Assam earthquake, but people from Tapponnier's group do look at the record associated with the Assam earthquake and find out that in fact the Assam earthquake in 1950 is not only just associated with the main frontal thrust that in the frontal part of the Himalayan mountains. They also may associate to another thrust fault in the frontal part between the Assam Valley and the Mishmi hills. This is the thrust fault that connecting all the way to the southeast and connecting to the Sagaing fault. All the white dot you are seeing in this figure are associated to the landslides. And the bigger the circle, the bigger the landslide it was back to the 1950s. So you can see that most of the big landslide are actually on the hanging wall of the Mishmi thrust fault. It is a strong indicator that the Mishmi thrust fault must be one of the source for the Assam earthquake. So back to about 2018, 2015, they actually had a chance to went to the Assam Valley to look for the feature associated with the Mishmi thrust fault. And this is the fault scarp that they can see next to the river cut. And on top of these terraces, there's a very thin of the gravel covering, which indicate this is the previous riverbed before the earthquake happened. And the height of this scarp can reach to about 7.6 meters. And this is just the vertical stroke of the thrust fault. If we use the 30-degree fault angle, then the 7.6 meters basically means that we may have about at least 15 meters of slip on the Mishmi thrust when the Assam earthquake happens. In some place, you can see the scarp is much higher, which means that the slip of the Mishmi thrust may much greater than just 15 meters. So they also see the scarp in the frontal part of Himalayas, but actually the scarp is not as high as the Mishmi thrust. So this indicates that the Mishmi thrust may be the major contributor to the Assam earthquake, whereas the main Himalaya frontal thrust play a minor role. So when they are trying to compile all the different records and using the seismological record to construct the focal mechanism and add them together, they find out the majority of energy actually indeed released from the Mishmi thrust, and that explains the distribution of the landslide on the hanging wall of the Mishmi thrust. And as well as the aftershock distribution associated with the Assam earthquake. It's worthwhile to note that although in general, we believe the Sagaing fault right here did not involve in the Assam earthquake, but we do see a lot of the landslide happening after the Assam earthquake, in the northernmost of the Sagaing fault, which has an indication that either the rock close to the northern Sagaing fault is weak and prone to the landslide, or actually the northern tip, the very northern tip of the Sagaing fault has been triggered and induced during the Assam earthquake. So before the Assam earthquake, there was another very large earthquake happening close to Myanmar, which in fact is happening at the northern border of the Bangladesh, in the Shillong Plateau. The Shillong Plateau is a very interesting location because the Shillong Plateau itself was composed by Cambrian to Precambrian massive crystalline rock, which in fact are associated with the major composition of the Indian continent. But around the Shillong Plateau, all we can see is a very late Cenozoic sedimentary rock. And Shillong Plateau itself has been exhumed to more than 1,000 meters high and with the very old rock exposed. So what controls the exhumation of Shillong Plateau? It is likely because that not all of the strand between the Eurasia and the Indian continental collision is absorbed by the Himalaya thrust fault. Instead, in the southern end of the Shillong Plateau, there is high-angle reverse fault or the thrust fault we call the Turkey thrust, may starting to play an initiation of a subduction in the northern south of the current plate boundary. So maybe this is just a proto-plate boundary or a baby plate boundaries. And here in 1897, a great earthquake happening in this area. And this is again the map, the macroseismic map drawn by Oldham back to 1899. And you can see that from the hilly area to the Rakhine state, that the earthquake was greatly felt in the western part of the Myanmar. The other thing we noticed is the very high intensity zone is forming a bell shape, whereas along the Daki thrust, the high intensity area is well aligned with its locations. These are all the photos that taken after this late 19th century earthquake. And you can see that all of this village that was originally built on the hillside was slumping into the ocean. So it indeed caused a lot of issues in terms of landslide and the human losses because of the strong ground motion. The interesting thing about this earthquake is that the British people actually have a very nice triangulation network surveyed before and after the earthquake. And strikingly, what they are seeing is that the northern edge of the Shillong Plateau, there is a place where they see a great shortening happen. And the amount of shortening can reach to about 7 meters. So in the past 20 years, there's a group of scientists believe that, in fact, although Daki fault is a major active fault in the southernmost of the Shillong Plateau, however, the 1897 earthquake, in fact, was happening on the Backstrap fault, which was named to the Oldham fault. However, the paleoseismological observation shows a completely different point of view. Whereas a Japanese scientist find out in the south, along the Daki fault, there are several places that we can see the stratigraphy was tilted around the late 19th century, which is likely to be corresponding to the Shillong earthquake. So there is still a controversial between what is the source of the Shillong Plateau, a magnitude 8.1 earthquake. So the previous two earthquakes we talked about is around Eastern Himalaya syntaxis, the center of the syntaxis, and in the southern part of the Shinlong Plateau. Now let's shift to the target to another major strike fault in the China territory. This is the Xianshui and Kyaukkyan fault system. This fault system it's a lateral fault system, but its behavior is very similar to the Sagaing fault that all of you are familiar with. If we look at the historical record from China, you can see there is a series of earthquakes happen in around 14th century along the Xianshui Kyaukkyan fault, as well as there is another sequence of earthquake up to magnitude 7.5 happening in the 18th to 19th centuries. So this is one of the major seismic sources in the southern part of the Sichuan Basin all the way to the Yunnan area. How about the situation inside the Myanmar territory? This is one of the great examples that happening in the 1912 in close to the city of Dongji. So back to the beginning of the 20th century, Tony Brown drew this very well-drawn intensity map showing that the 1912 earthquake was felt all the way from Mandalay to Yangon and even to Bangkok, with the strongest intensity happening close to the Kyaukkyan village. However, back to the old time, if we look at the old seismological record, the original magnitude of this earthquake has been determined to magnitude 8.0, which maybe indicate it was a super large earthquake associated with the strike fault that need to have a length more than 300 kilometers long, just like the Wenchuan earthquake. However, in the past 15 years, there are several different groups of people went to the field trying to look for the evidence of active faulting associated with 1912 earthquake. And there are only very few locations where we may be able to see such kind of evidence. For example, the UK group went to the area near the Kyaukkyan village, and what they see is that the railroad built the beginning of the 20th century actually show a very good bending of the rail. The bending of rail track is around 2 meters. So 2 meters of bending in the Kyaukkyan village, saying that maybe the earthquake is not as large as we previously thought. The earthquake may not as large as we previously thought as a magnitude 8 earthquake, because if it's a magnitude 8 earthquake, we may expect we're seeing the deformation that up to about 5 to 6 meters in a strike fault system. However, in this case, that the most obvious deformation is only around 2 meters. So the question that arose at the beginning of 21st century is how large was the 1912 earthquakes? Using all the old data, you can see that from the old tables that at the middle of the 20th century, we believe it's a magnitude 8 earthquake. And now, starting from 1980s, we're starting to revise our record and think maybe the magnitude is slightly smaller than magnitude 8. Maybe it's a magnitude 7.7 to 7.6 earthquake. And around 10 years ago, what we did is that we are trying to use a record that compiled by Cornish Brown in the beginning of 20th century to reinterpret its ground motion across the Myanmar. And what we are seeing is, in fact, although the epicenter was located near the city of Dongji, but in fact, the very strong intensity only appeared in the northern part of the Kyaukkyan fault, close to the Kyaukkyan village, whereas the intensity in Dongji city, as well as the Pindaya and the other city to the south, is only reached to intensity 7 and 6. And intensity 7 and 6 are not usually associated with the surface rupture of the active fault. So if we are using the length of the intensity 8 area, it gives us about 160 kilometers long rupture, which indicate the magnitude, in fact, may only be about 7.6 rather than a magnitude 8 earthquake. So, based on the modified seismological record and also the intensity record, now we believe the 1812 earthquake is not as large as the Shinlong earthquake nor the Assam earthquake. Instead, it's a magnitude mid-7 earthquake. And does this kind of mid-7 earthquake also happen in the northern part of the Shan Plateau? It is very likely. One of the very good example is the Lantang earthquake happening in China, close to the border between China and Myanmar. The Lantang earthquake, the magnitude was determined to be using seismological record. It was determined to be a magnitude 7.3 to 7.6 earthquake. It was happening along the Lantang Fault, which is a right lateral fault, extend for more than 200 kilometers. Right after the earthquake, our Chinese geologist, our Chinese colleague went to the field to survey the damage of the buildings, the ground deformation, and try to come up with the idea about the extent of the damage after the Lantang earthquake in 1988. And this is the strong intensity area they are seeing. You can see that the strong intensity area are mostly linear, forming a lineation extending from the northwest to the southeast. And this direction is very similar to the Lantang fault that we draw from the geological map. And along the Lantang fault, there are a lot of different features that you can see from the topographies. For example, we are seeing a lot of ground cracks. We are seeing opening of the feature, and the gravens indicate there's a lot of additional feature forming on the ground. In some places, we are even seeing this kind of offset, indicate the right lateral offset and sometimes the left lateral offset. As I already mentioned, the Lantang fault is a right lateral fault. So those left lateral offset are most likely to be associated with the anti-Rideau shear, which is orthogonal to the main fault trace. And using this type of record, they draw a ground deformation map along Lantang fault, indicate that most of the deformation they see across the fault are ranging from about 80 centimeters to up to about 2 meters across the fault. And 2 meters deformation is about the right amount of strike slip offset for a mid magnitude to the lower to the mid magnitude 7 earthquakes. So now we know that in northern part of Shan Plateau, there are examples from the 1912 and 1988 that the earthquake magnitude can reach to about mid-7s. But how about other events? Are there any other recent event indicate that the earthquake magnitude can be high? Actually, no. Most of the earthquake, except for the two earthquakes we mentioned in northern part of Shan Plateau, is actually magnitude 6 to magnitude 7 event, instead of the magnitude 7 and above event. For example, on this map, there are two different earthquake clusters shown along the Meichang Fault and the Namman Fault. The earthquake happening in the Meichang Fault is a mid-magnitude 6.3 event at the center of the Meichang Fault in the Laos area. In 2011, there is a damaging earthquake happening in the Myanmar side that destroyed the town of Tarlay and several villages in the mountains. This is a magnitude 6.8 event. So again, it did not reach to magnitude 7, and it only associated with the rupture of the westernmost of the Namman Fault. And when the geologists went to the field, this is what they see across the fault ruptures. So you see the paddy field burn was offset for about more than 1 meters with a very clear trace. This is the feature that we call the mold track across the fault. And not only that, you can see this field burn has been twisted or walked close to the fault trace. So indicating not all of the strain is accumulated right across the main rupture. Instead, they may have some strain is distributed in the soft material close to a surface, close to the ruptures. Because this is a very recent earthquake event, we not only can use the field measurement to measure the length of the fault and the deformation associated fault, we can also use the radar image to sense the extent of the rupture and amount of the deformation across the active fault. And the figure to the right is the diagram we call the differential INSAR, or we call it D-INSAR. And all of these colored rainbow bands indicate the amount of deformation before and after the earthquakes. And the denser the rainbows, the larger the offset it is. So as you can see from this map, the rainbow actually are closed or merged to the tip of the active fault along this red line, indicate that this segment of the non-mom fault, in fact, was ruptured in the earthquake, and that's a smoking gun of the 2011 Tarlay earthquakes. About further to the south, in 2014, there's another damaging earthquake happening in Thailand, which we call the Chiang Rai Earthquake. Compared to the Tarlay earthquake, which is a magnitude 6.8 earthquake, this earthquake is much smaller, only a magnitude 6.1 to 6.3 earthquake. And as you can see from the Thailand Meteorological Department's earthquake catalog, the aftershocks are circling around this part of the mountain range where we did not see a very clear active fault on the surface. The seismologist is using the very detailed local seismic network. They can try to relocate the distribution of active fault. And after the relocation of this aftershock cluster, they see not only the main fault, this fault was ruptured for about 20 kilometers long, but also there's another orthogonal fault, the conjugate fault, also ruptured during this earthquake. So in the northern Thailand and Myanmar, there are a lot of this kind of conjugated fault system that both can be ruptured during the earthquakes. So if we compile all of this earthquake and rupture location in northern part of the Sunda Plate, this is the map that we made around 10 years ago. That as you can see, all of the blue boxes indicate a potential rupture patch along the active fault. Most of the earthquake happening in the 20th and 21st century did not involve the wholesale rupture of the entire active fault. For example, close to the Mogok, the Nandinghe fault, which is the active fault with the length about 360 kilometers long. Only a very small portion was ruptured in the 1941 and generating a magnitude around 7 earthquakes. The rest of the fault are still not ruptures, which means that in the future, they have a high potential to rupture and generate bigger earthquakes. And the other thing that we notice is that for most of the active fault, its length is far larger than the rupture extent. That means that in this area, there's still a lot of energy haven't been released through the earthquake, and they are waiting for another big earthquake to happen in the near future. So from all of this earthquake and deformation, how can we infer it to the beginning of our conversation or this lecture about what is the cause of the ground deformations in this area? From the earthquake point of view or from the fault distribution point of view, we are only seeing a very deformation in a very shallow surface. However, these two models has completely different implication about how the shallow surface deform. So maybe they can give us some clue about the implication of the bigger tectonic pictures. The first thing that we're seeing is the distribution of active fault in northern part of the Sunda Plate. You can see that all the purple line, in fact, are the left lateral fault. They are distributed parallel from one to the others. And they are bounding by right lateral fault. This is a very classic example of so-called bookshelf faulting, where the boundary is controlled by major trade boundary active fault. And in the interior of the block, there are several active fault, which is smaller active fault with a different slip sense. And you can imagine that the Red River fault and Lantang fault, in fact, are playing like those boundary fault. So this area is a Red River fault and Lantang fault, and here is the Kyaukkyan fault and the Sagaing fault. And right in middle, the block in middle are all the left lateral faulting, which are all the left lateral fault in between Myanmar and Yunnan. So if the ground deformation can be explained by the bookshelf faulting, how about the GPS velocities? Back to the old time, when the geophysics looking at this map, what they are seeing is that between Myanmar and the Sichuan Basin, there is a band of the area where the GPS is moving faster in the middle and moving slower at the boundary. And they infer it to channel flow, just like a water channel. However, because there are so many dense distributed active faults, we can also use the elastic deformation to making a curvature to explain all the deformation we are seeing from the GPS. So this example tells us the GPS velocity is not a conclusive evidence to show there indeed is a crustal flow happening between China and Myanmar. Even worse is that originally the geophysical evidence showing that there is a very weak lower crust between the southern China block and Myanmar. But now what we're seeing is that this deformation, this low velocity zone or weak crust kind of localized and did not across the entire area. So maybe the deformation we're seeing here is a combination of some part has been flowed and the other part has been extruded like the block and forming a bookshelf fault system in the northern part of the Sunda Plate. So that come up with three different end models to explain deformations. The first is everything is controlled by the bookshelf, but this model cannot explain that we're seeing localized distribution of soft lower crust from China to Myanmar. The other model is that we may be able to explain everything by localized channel flow in the lower part of the crust. However, this cannot explain the distribution of active fault on the surface very well. So because of that, we may need to have other mechanism to driven the crustal deformation, which may be associated with the upper part of mantle, that because of the retreating of the Indian slab, we may have a sensosphere flow that flowing from the mantle beneath southern China to the mantle beneath the Myanmar block. This kind of the mantle flow has been inferred from the plate model. For example, this is one of the plate model, simplified plate model showing that how the retreating slab may stuck the mantle above to flowing into the Burma plate. So you can see all of these vectors are pointing out that the topography and the ground deformation the mantle flow may be associated with the retreating of the Indian slab. However, because the mantle was happening about 50 kilometers below the surface, at least, it is very difficult to prove such kind of mantle flow exists or not. So we may need to use a lot of different modeling to point out indeed indentation of India may cause such kind of corner flow around the eastern Himalaya syntaxes, and that corner flow may cause the deformation in the upper plate. And to do that, we actually need a lot of different evidence in the future to prove which model is correct. For example, we may need a better model imaging where is the Indian slab beneath Myanmar and northern Sunda block, and how the slab was acting. For example, if the slab is retreating or it's advancing, or the slab was broken or it's not broken, we need a very good resolution of such kind of remote imaging for the upper mantle to prove that. As for the geologists, we also need other type of evidence. For example, the paleomag evidence to show there is a plate rotation, a blood rotation happening in the northern part of Sunda Plate, to having a serious Uranian sovereign dating or Uranian lead dating to show the volcanic activity, the evolution of volcanic activity associated with this slab. And this requires a lot of field work and lab analysis, as well as international collaboration to figure that out. So let's go back to the figure I showed at the beginning. We are leaving the northern part of Sunda Plate and eastern Myanmar are situated in a very key place to help us to resolve the puzzle about how the Tibetan Plateau and how the northern part of Myanmar is deformed in the past several million years. And to solve this issue, we need a lot of different collaborations to really help us to resolve whether block extrusion model can well explain the deformation in this area, or we indeed need to have a lower crustal flow to explain the deformation in this area. So I will end my talk here, and thank you for everyone's listening. Thank you.